I'd like to take a moment now to summarize what we've seen with boosting and what impact it's had in the real world. Let's talk about AdaBoost. So AdaBoost is one of the early types of boosting algorithms, extremely useful, but there are other algorithms out there. In particular, there's one called gradient boosting, which is slightly more complicated, but extremely similar. And it's like AdaBoost, but it can be useful not just for basic classification, but for other types of loss functions, for other types of problems, and it's what most people use. So gradient boosting, it's kind of a generalization of AdaBoost, you can think about it that way. Then there's other related ways to learn ensembles. The most popular one is called random forests. So random forest is a lot like boosting in a sense that it tries to learn an ensemble of classifiers, in this case decision trees, but it could be other types of classifiers. And instead of using boosting, it uses an approach called bagging. And just very briefly, what you do with bagging is you take your data set and you sample different subsets of the data, which is kind of like learning on different sub-data sets, and we learn a decision tree on each one of them, and you just average the outputs. So you're not optimizing the coefficients W hat, and we're learning from different subsets of the data. It's easier to parallelize, but it tends to not perform as well as boosting for a fixed number of trees. So for 100 trees or 100 decision stumps, boosting tends to perform better than random forests. Now let's take a moment to discuss the impact boosting has had in the machine learning world. And hint, hint, it's been huge. It's amongst the most useful machine learning approaches out there. It's useful in a wide range of fields. So for example, in computer vision, a lot of the default algorithms in computer vision use boosting, like face detection algorithms, where you take your camera, you point it at something and tries to detect your face of who is there. That uses boosting, extremely useful. If you look at machine learning competitions that have become very popular over the last 2 or 3 years, from places like Kaggle or KDD Cup, most winners, so this is more than half, I think it's about 70% of winners actually use boosting to win that competition. In fact, they use boosted trees. And this looks at wide range of tasks like malware detection or fraud detection or ranking web searches, and even like interesting physics tasks like detecting the Higgs boson. All those problems and all those challenges have been won by boosted decision trees. And this is perhaps one of the most deployed advanced machine learning methods out there, particularly the notion of ensembles. So for example, if you know about Netflix, which is the kind of online movie place where you can watch movies online, it's a kind of company. They recommend what movie you might want to watch next. That system uses boosting, actually uses an ensemble of classifiers, but more interestingly, they had a competition a few years ago where people tried to provide better recommendations, and the winner was one that created an ensemble of many classifiers in order to create better recommendations. So ensembles, you'll see them everywhere. Sometimes they're optimized with boosting, sometimes they're optimized with different techniques like bagging, and sometimes people just by hand tune the weights and say, okay, I'm going to give one to this, half to that. I don't recommend the last approach, I recommend boosting as the one to use. Great, so in this module, we've explored the notion of an ensemble classifier, and we formalized ensembles as the weighted combination of the votes of different classifiers, and we discussed generally the boosting algorithm, where the next classifier focuses on the mistakes that were made so far, as well as AdaBoost, which is a special case for classification, where we showed you how to come up with the coefficients of each classifier and the weights on the data. We discussed how to implement decision stumps, boosted decision stumps, extremely easy to do, and then talked a little bit about the convergence property of how the training error boosting tends to go to 0, but you have to be concerned a little bit about overfitting, although it tends to be very robust to overfitting practice.